Let's talk about something that's happening all around you right now. It's this invisible, high-stakes battle being fought every single second to keep our entire power grid stable and, keep the lights on. All right, let's dive right in.
You know that moment, right? A big storm's raging outside, the wind is howling, and for just a split second, the lights flicker, and then they snap right back on. It almost feels like a little bit of magic, but it's not. It's some seriously impressive engineering.
That little flicker, that wasn't just a random blip. That was the sign of a massive, high-speed battle that just took place. The grid just fought off what engineers call a fault, a sudden, really violent disturbance. We're talking a lightning strike, a tree branch smacking a power line, you name it. And in that one instant, the entire system had to react, and it had to react perfectly to avoid a total collapse. So, how in the world does it do that? Well, it all comes down to maintaining this perfect, incredibly delicate balance. And this is the absolute core principle of keeping our grid stable. I want you to picture the power grid like a perfectly balanced scale, okay? On one side, you've got all the power being generated by power plants, and on the other, you have all of us. Every light bulb, every phone charger, every factory, everything using that power. As long as generation equals demand, everything is great. Power flows smoothly. But if a fault suddenly knocks out a major line, that scale tips, and it tips violently. That's when you're staring down the barrel of a blackout. Now, the main villain in this whole story, the thing that makes this balancing act so incredibly difficult, is something called reactance. The easiest way to think about it is like electrical friction. It's like a bottleneck in the power lines that's always resisting the flow of power. And during a fault, that bottleneck becomes a huge problem, pretty much choking off the energy the system desperately needs to get itself back in balance. So, for the engineers trying to keep everything running, here's the crucial takeaway. While you could try to build bigger, heavier, more powerful generators, the most practical, the most economical, and really the most viable way to make the grid more stable is to just go on the attack and reduce that reactance. And lucky for us, they have a whole toolkit of proven methods to do exactly that. So let's take a look at some of the classic, time-tested ways that engineers defend the grid. To lower that electrical friction, one thing you can do is use duplicate, parallel lines. It's kind of like adding another lane to a highway, right? It just helps ease the traffic flow. They can also install these devices called series capacitors, which, well, they essentially cancel out some of that pesky reactance. Or you can even physically change the lines themselves by bundling the cables together. Each one of these methods just makes it that much easier for power to flow where it needs to go. But here's the deal. Reducing reactance is only half the battle. The other part is speed. Because that reactance is choking the power flow, the whole system becomes incredibly fragile during a fault. That's why you have, and I mean this literally, mere milliseconds to isolate the problem. Modern high-speed circuit breakers can detect a fault and physically disconnect that part of the grid in just a few cycles. We're talking fractions of a second, to stop the instability from spreading like a virus. And what's really clever is that most of these faults, like that tree branch hitting a line in a gust of wind, they're temporary. So an auto-reclosing breaker will pop open to clear the fault, it'll wait just a moment, and then it automatically tries to close again. Most of the time, the branch has swung away, the fault is gone, and the power is back on without a single person having to lift a finger. It's a really simple idea that just dramatically improves the grid's resilience. Those traditional methods are incredibly powerful, for sure. But now they're being backed up by some truly cutting-edge technologies that are, well, they're completely changing the game. One of the biggest game changers is high-voltage DC, or HVDC. A traditional AC grid is like a huge team of synchronized swimmers. Every single part has to be perfectly in step, perfectly in sync. If one person messes up, the whole routine can just fall apart. But an HVDC link, it's asynchronous. It basically acts like a firewall between two different systems. So a fault on one side is completely isolated. It just can't cascade over and take down the other side. It's like having two totally separate highways instead of one big, interconnected mess. Okay, check this out. Here's another incredibly fast-acting solution called fast valving. So when a fault happens, the electrical load on a generator suddenly vanishes. But the massive turbine is still trying to pump in huge amounts of mechanical power. This mismatch is bad news. It makes the generator speed up dangerously. Fast valving detects this imbalance, and in an instant, it partially closes a valve to reduce the steam hitting the turbine, perfectly matching the mechanical power to the new lower electrical demand. It's genius. And hey, if you can't reduce the power going in fast enough, you can always add an artificial load on the other side. That's exactly what a braking resistor does. You can literally think of it as an emergency brake for a generator. When a fault makes the electrical load disappear, the control system instantly connects the generator to these giant resistors, which act as a temporary fake load. This braking action gives the system precious time to clear the fault without the generator spinning itself to pieces. And if we look even further into the future, researchers are developing some amazing new tools, like superconducting fault current limiters. The idea is to place these at critical points in the grid so they can almost instantly absorb the massive surge of current from a fault, basically smothering it before it can ever cause the system to become unstable. So when you start to put all of these pieces together, the classic methods, the modern innovations, you begin to see the grid for what it really is. It's a true engineering marvel. I mean, the sheer scale of a modern power grid is it's almost impossible to really wrap your head around. But its incredible resilience, its ability to withstand these constant attacks from nature and equipment failures, is built on the very principles we've just walked through. It's that constant balancing act, the endless fight against reactance, and that absolute non-negotiable need for speed. You know, the field of power system stability is vast and deeply complex, but by understanding these fundamentals, you've really taken the first crucial steps into this incredible invisible world. And all this leads to a final, really critical question. As we add more renewables, more electric cars, and just more complexity to the grid, the challenge of maintaining that perfect balance is only going to get tougher. What new invisible battles will need to be fought? And what brilliant new solutions will engineers come up with to keep our electrified future stable?